So let's start with the first thing for now. So minimize this to the side. This button on, hope for the best. Okay. So the first thing I wanted to talk about this morning has to do with something called algorithmic analysis. Right. So what we're going to do is just recap Piggle and complexity in general, and then let's look at some example programs and let's analyze those programs. Right. Okay, so Piggle, I just kind of stole this slide from the first lecture session. And to just kind of recap, Piggle was all about the growth of algorithms as usually some kind of thing increases, like the input, for instance. So if you like your algorithm was depending on working everything in an array, as the size of the array increases, what happens to the runtime of the algorithm, or runtime, the memory, in our case, right? So big O notation just tells you about how fast an algorithm grows, and it's an asymptotic group. Right. Again, this one is also stolen from the first lecture. Just to give you an idea of if you have different algorithmic complexities. So somebody one we talked about so far was logarithmic, log base 2 of n, linear, O of n, linearismic, which is n log n, quadratic, right? And in general, polynomial type things. One that we did talk about and I don't have on this slide is exponential, that's 2 to the n. And then on the upper end is n factorial, right? Factorial type. And here is the last slide of stolen from morning, which is giving you an idea of how each one of these algorithms grow. Right, so you all get the idea of this, right? Just making sure before we move on. Just a quick recap on what we were looking at. Yeah, apologize if I'm not sounding too well. I actually have a fever, so if I'm not sounding too clear, just tell me, right? So everybody, I hope, got this idea. So let's test to see if we actually understand this idea. So let's kind of get all these slides for a second. Let's leave that be. And what should I use? Okay, let's go with Excel. Just some ideas, right? Okay, let's open a blank workbook here. And let's say I have in this corner I have n, right? So let's go with various thoughts, right? I just go and start and put it down in orders of 10, right? And 1,000, 100, 1,000, 1, 2, 3, 4, 5, 6, a million. Let's go with that. So if I said log base 2 of n, this will equal to log of this number base 2. Let's kind of copy that across, right? So this is just idea of log, right? So, and then if I just did n itself, let's go, this is just equal to this. Right. So what happens if I just plot these things versus n, right? Let's see, can I do that? Is that? Ooh, there we go. So here's a quick chart of how it looks. Let's see if we can just make it a little bigger. You all can see that, right? I assume. Okay. All right, cool. So you also see a difference between like how linear scales as opposed to logarithmic. It's like heaven and earth kind of thing. Actually, what if we add in n squared? Just out of curiosity, right? It's equal to this times so. Let's see how that looks on the same axis. I mean, it's supposed to just look just like the one from before. Let's just see this is. All right, cool. So you can't even see log base 2n on these axes anymore. Right? It's kind of hard to see because of just the growth rates and how big it kind of jumped up. So what I'm going to do is I'm going to click here on the bottom and just meddle with the axes, right? So on the axes, I will change the axis to be on logarithmic scale. Yeah. And let's do it for both axes. That's just formatting the axes, so it'll just be easier to see. So I want you to notice what does this look like to you? So I call a log axis. It's easier to see, right? I hope. Not change the axis scale. Anyways, what I wanted to notice is that each of these have like a different looking kind of gradients when you look at it on this log type scale. We agree with that, right? So what a log scale actually allows you to do is see how these things change um with the different complexity orders. So what I'm trying to bring up here now is why these particular things in general. Why these particular things? Why O log n, why O of 1, why O of n, why O of n squared, exponential? What's so special about these functions? Ideas?
So repeat the question, please.
So here we have like 3 different things, right? And we saw these in the complexity orders, right? I'm trying to figure out what's so special about log base 2n versus n squared. Why these functions in particular? Why are these functions highlighted in general?
Well, they could be used to represent time and space complexity. So like the algorithm, the exponential ones have a higher time complexity, where the log ones is kind of like the opposite of exponential. So whatever
Well,
complexity it is, it would be the reverse direction or shorter time.
well, that's accurate, but I'm trying to get into why are these um good functions used to demonstrate complexity? Well, the bottom line is the reason is because each of these shows like a different, literally, order of groups, right? The growth of these look nothing alike, right? And I literally had to put this on a log axis to be able to see the difference in the scale of groups. And perhaps that's not too clear. So what I'm going to do is, so O of 1 is actually one complexity order, right? So let's say, let's go with 1, right? So if I plotted this on this graph, what's that going to look like?
A flat time because they constant time.
Yeah. So it's just going to be this kind of flat line on the bottom here. Watch how these look compared to the others, right? Constant time. All right. But what about constant time in general, right? Does constant time have to be 1 or could it just be like a random value? So let's say
Two.
instead, yeah, instead of it being 1, let's say it was 1,000. So what okay, well, ignore the base value because it's screwing up this time. Yeah. So it doesn't get confused. It's getting confused until the 1 was a value to plot. Okay, watch how this thing looks, right? The blue is the constant time one at the moment. I had just selected 1,000 just randomly. What you notice about this graph at the moment?
It's that some of them have actually started with a better runtime than constant time for
Hmm.
quickly becoming worse.
Right. So sometimes there are some algorithms that have like a bunch of statements in them, right? And therefore the runtime is actually pretty bad, but it doesn't scale at all. It just remains constant at that whole thing. The idea again is with all of these different complexity things is that over time, they will overtake it, right? Even this logarithmic one, if I plotted it for long enough, it would overtake this constant time one. Yeah. So that's the first thing I want to draw to your attention, that if you had just a constant value in it, even if that constant value was large, all of the other ones, because they depend on n, will overtake it for a significantly sized n. That I hope makes sense, right? Just going to delete this one for now. I think something went wrong with my data. Is 3. We'll delete this and redraw it because clearly something went wrong, right? Let's kill the n squared for a second. Just let regenerate search chart reference. Oops. Oh, on this actually on. Let's make it back log. Here as well. You know, I don't really like Excel. Do these kind of funny things sometimes. Anyways, at least let us do what we want to do, right? Really what we care about. All right, cool. Anywho, so the thing that we saw just now is that with constant time, it doesn't matter where that is, all the others will kind of overtake it over time. Is that a good thing? I know it sounds like a kind of weird question, but um, I guess the question I'm trying to ask is whether this O notation makes sense as a thing to do for runtime. That's like ignoring that constant factor. Thoughts?
So I was thinking no.
Well, it's literally something you have to take with a kind of grain of salt, right? Again, you just have to keep remembering that it goes about growth and nothing else. It doesn't tell you anything else other than growth. So let's say we went with another thing, let's say is 2n plus 10, something like that. Let's go 2 by this plus 10. I'm making up some values here, right? And let's plot this one on this graph and see what happens. It's a, let's go with G instead. So this 2 by n plus a constant. What's the growth of this one look like? Is the growth different to the n version?
It's basically the same thing, it just doesn't have a different y-intercept.
Yeah, pretty much it, right? So this is something I want you to get at, right? If you multiply by 2 or r constant or anything like that, it does not change the growth. The rate of growth is not affected. It's the same rate of growth, more or less. Obviously, the 2n plus 10 is a worse rate of growth, but what you conclude is they both have the same order. Right? That's the point of this one, right? In fact, let's be even more crazy, right? Let's go by 10 by n, and I'm going to add the log 2 of that. Would that meaningfully change anything? So 10 by n plus that thing. Yeah, I just basically added the log base 2 of that. What's that going to look like now? Does that look any different to this n growth?
Not really.
Not really.
No, it's the same growth
It's
rate.
the same groups. So here's the thing: when you add in the complexity of something else, so let's say, so what add actually means is that your algorithm had the first part, and the first part was, I don't know, maybe you're printing out everything in an array, so or n, and then you had like a binary search after or something. The sum of those 2 times, because that'll be overall time, is going to be dominated by the linear groups, right? The log being a whole scale factor less in terms of complexity will not meaningfully add to your runtime as it grows. It doesn't. It simply doesn't. That's actually one of the reasons we use these complexity classes, because each class actually represents a different growth order. So when we sum them, the more dominant one will prevail. So if you were to get an algorithm where it had a linear growth, and then right after it, you run a next function that happened to be logarithmic, we simplify that as a linear growth overall. And the reason we simplify it is because compared to the linear growth, the log 2 is not going to add significantly. Again, that's why we have these complexity classes. So again, let's consider this one now. What if we have n times n? N times itself. Yeah, which is n squared. But I just showed you how they ended up with these complexity classes, right? Okay, look at where the n squared is. This is a totally different gradient to the ends, right? So it's a totally different growth order. So basically, when you multiply complexity classes, you get a different growth order. Does that make sense?
Yes, sir.
Right, cool. So obviously this n squared is actually worse than this n, right? And all the derivatives of the n here, right? And clearly it's also worse than this log 2n. So what would happen if you actually multiply this n and multiply that by a logarithmic? what kind of complexity class you'll get?
The n my dominators.
Nope, we're multiplying two complexity classes together. Right, this is a different thing. Right, so let's see. Well, let's see what it looks like, right? Step G there. Bam. Yeah. Watch this. This gradient different from the n gradients. Yeah. Watch, they kind of cross over this point. So therefore it is not significantly worse, but it is worse. Is that making sense now? So instead of like adding, so when you have adding, you'll have something that's obviously dominating. But when you multiply two complexity classes against one another, you will get another one that is worse than the worst of the two. So in this case, you'll have something that is worse than n. But notice that this is better than this n squared, right? Because this is n squared is actually n times n. But this one is n times log n. So therefore it is worse than n, but better than n squared. You see how we got that? So by that same kind of logic, if I did n squared times log n, that will be worse than n squared, right? If I said n times log of n, obviously, equals with this times n. Like this data. Page back. Okay, here to see this one is actually a little bit worse than this n squared. You can't see it too well, but notice this point here is a lot closer to than these, right? Actually, it's growing a little bit worse, but because it's a log, it doesn't grow significantly worse. But it is worse, right? So we can't approximate this to n squared or anything like this because the n squared times log is actually a bit worse. So then what would we expect for n cubed? That's n times n times n. Is equal to n squared times n. So I would expect n cubed to be worse than n squared log n. Just thinking about it a little bit, right? So yeah, I see. To see how much worse n cubed gets. So the takeaways I want you to get from this is once you are adding, meaning you have one algorithm of one order followed by another algorithm of the next order, then the dominant term will prevail, right? So if you had O order n plus some constants, that will just be order n. Or if you had order n plus lower complexity, then that will still be order n. Similarly, if I did this n squared and I added n to this n squared, then the n squared will dominate it, right? So once you add it, the lower complexity one doesn't add anything meaningful. But once you start multiplying, then you end up with another growth rate, with something that's a little bit worse. Make sense? And multiplying by a constant obviously doesn't change anything, right? Because a constant is literally just that, a constant. It means that there is no change, right? It doesn't grow with n. So multiplying by a constant is a special case because it is a complexity class that actually means that, well, this is constant time. So it does not change the order with respect to n. But once you multiply two complexity classes together, that is, both of them are not constant time, then you'll get something a little bit worse than the worst of the two. Make sense? Go with it? Or this explanation was worthless.
Yeah, it makes sense.
So let's head back over to these slides. Yeah. So again, this is why n log n, see the multiplication of these two, they got something worse than n. Right. So this is not on a logarithmic, say, see in the terrible roots. So see, linear arithmetic is actually worse than the n squared. So n cubed would actually be worse than n squared, and n to the 4, n to the 5, n to the 6 would all be in this kind of area right here before the exponential, right? So if you had n to the 1,000 even, it's not going to even get close to this exponential one, right? And if I took this 2 to the n and multiply that by n even, it's still not going to approach the factorial, right? That's the reason they chose these particular classes, because they showed literally different orders of groups, and multiplying by them will get you worse, and this adding will not change the price of X. Yeah. Cool. So now let's try to see if we could put other way around. That's if we could actually come up with the complexity based on the code. Right? Slightly different tactic. I think in these slides, I just literally did the first one for you. So let's just kind of walk through the first one, and then you will help me out with the other ones, right? So let's go from the side. Yeah, let's say that. Click. Good. All right. So the first thing we're going to do is something called a microanalysis. There are two ways we could approach this. There's either microanalysis, or we could do a macroanalysis. Right? I think sometimes starting with micro is easier from an explanation point, even though it's a lot more long-winded. So let's try to figure it out for this function here on the left. Right? So what we're going to do is, you notice in this list here on the right, let's classify how much time it takes to do specific statements in C. So we'll write down the letter A, milliseconds, if you have an assignment. So like this sum equal 1, that's an assignment operation. If you can 1, I put it in a sum. Yeah, put in a B if you have a evaluation of a Boolean condition, like this comparison here, I is not equal to size. Okay. S you put down for any addition or subtraction we have in here, M if we have any multiplications, and P for an increment, right? Which is roughly A plus S, because increment, that's like I plus plus or plus plus I. It is equal to addition, meaning S, plus an assignment. You put it back into the I, for instance. Okay. So let's do a microanalysis on this piece of code here. Right. Now to do it, the first thing I will do is just rewrite the for as a while, right? Because it's a little easier to see with a while loop than a for loop. Because some people get a little tired with a for loop, right? So obviously with a for loop, this statement, the first thing has to happen before the loop. Then the while is with this condition here, and then this plus plus I has to be the last thing in the while. So as you can see, I made no meaningful change to the code. I literally just wrote it out in such a way that it'll be kind of easy to see. Right? Then the next move we're going to do is we're going to put down the timing for each one of these lines, right? So how much time the first line takes? A. So the second line will be A as well. Then you have this comparison here. B. This is a Boolean. Then you have these two increments, which is 2 P's, right? And that's pretty much it, right? So if I wrote that down, that's basically what it looks like. Right, everybody with me so far, right? So then if I wrote that down a bit further, then the total time for this code is the A plus A first, and then you have this B, and then 2A plus 2S. But the 2A plus 2S happens inside this loop. So the question is, how many times does the statements, the Boolean statement and the two increments run? How many times does that run? Any idea?
Around like the amount, the size of size.
Size of size. Okay, cool. That makes sense. If that didn't make sense to you, you can think about it in terms of what values of I actually exist in this loop, right? I will start with 0, and then it'll go to 1, then go to 2, and go to 3, yada, 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 until it reaches size minus 1. So the values of I is 0, and then 1, and 2, and 3, all the way to size minus 1. So how many things is in this set? Size, right? Because 0 counts as 1, and then the first thing I equal 1 is the second time it runs, I equal 2 is the third time, yada yada yada, go down below. Yeah. So the number of the same values of I is obviously size values. So therefore, the total time of this piece of code is 2a plus size times the sum of the times in the loop. Make sense? So if that is in fact the total time it takes, what do you think is the order of this algorithm? Big O.
Just n
Mhm.
the size.
So if size is representative of n, then obviously it's size times some constant plus a constant, which is just order n. Yeah. So in short, we could say that this thing grows linearly with increasing size of the array. Yeah. So microanalysis makes sense to you guys, right? I hope.
Yeah, understand.
So the obvious question I could say is, did we need to actually do the microanalysis to come up with this order n? Could we not go down to the nitty-gritty of having to add up every single line and still come up with the fact that this is order n? How would you do that? And you call that a macroanalysis. So rather than trying to add every single line in a microanalysis, what we have to do is take a step back and just look at this and be like, well, this is order n. Well, how do you come up with that?
They could just watch the while loop.
You could just watch the while loop. Okay, that's partly correct. I mean, it is correct, right? But I'm just trying to be a little bit what's the word? Pedantic. In that what you want to do, right, is you want to think about what would scale. So the first thing you have to do is think about what lines actually would scale as the thing runs, right? And obviously that would be the sum plus plus or the plus plus I, because that would change depending on how the loop is running, right? So what you actually try to do is figure out how many times the sum plus plus or the plus plus I happens, because that would give you an idea of the order, right? And obviously those will run size time. So therefore this is order of size or order n, right? Excuse me. Right. So that's your rough thing. So you could approach it either way. You could do a microanalysis or you could do a macroanalysis, whichever one you feel is easier for you to do. Sometimes some people find it a little easier to be nitty-gritty and go down into the nuts and bolts because you come up with the answer that way. Whereas some people could look at it and be like, well, yeah, what it is. So here's some for you to try. I didn't write the answers for the others. So let's give this a try. What is the order of this algorithm? You can either do a microanalysis or a macroanalysis, whichever one you prefer.
N squared.
N squared. So we have n squared. And you have the thickens.
Oh wait, that's one. I think it's 2n. It'll just be
Uh,
n.
Yeah, I think it goes on to n in this case.
Yeah, it'll go to n. And if that wasn't clear to you, what you'll notice is this for loop is basically the same for loop as before. So Well, give or take, right? It's just a slightly different decision on the inside. So clearly the line, if we're doing this as a macro analysis, that I'd be worried about is this line inside this particular for loop here, right? So this line occurs size time, right? But then look, you have a for loop that happens right after. And then if you're just adding up the times, you notice if you're doing a microanalysis, you would add up the times of these statements at the top here first, then you'd add the time of the for loop after, which was n. And then you would again add the time for this for loop again right after. So this one is a n, and this again working from 0 to size -1. So this statement happens as an n as well. This is an n, and this is an xn. So I would conclude that this is a function of n. But if there's actually 2n plus some constant again. Well, I'm not even going to use with 2 because you notice that this one has some summation and assignment, whereas this one has a multiplication assignment. So the amount of time each one of these loops take are actually different from one another. But again, that doesn't really matter too much because it's lower than n, right? Because that'll just be some constant times n, right? Even though it's two different constants. And I always add those two constants. And it'll still be a constant times n. So this was easy for everybody to see, right? I hope. If not, we try to develop the ability to see it easily enough. Anybody unsure? Or we move on to a slightly harder one. Anybody unsure? Okay, I will take that as nobody unsure. All right, so let's try another one. All right, so I need to do a macro analysis on this one.
It would be n squared.
Right, why you got that?
The for loop inside of the for loop.
Oh, that's not entirely wrong, but I can mess with you by giving you a for loop within a for loop that will not be n squared.
Well, how it works is that for every, let's say, value of I, you're doing the for loop, that is the second for loop in its entirety. This is happening for
Yes.
every single value of I. So that boils down to sort of an n squared situation.
So yeah, this is an n squared situation. Maybe I should give you an example where we have a double for loop and it's not going to be n squared. Okay, we'll come to that, I suppose. But yes, so the values of j for the second one is actually from 0 to size -1. So there are n values of j. The cout statement happens n time. Just looking at the inner for loop. For when I is 0. And then that n times will happen for I equal 1. And then that n times will happen for I equal 2. All the way up. So n times n is what you end up with here, right? So yes, this is an n squared in a nutshell. Again, the line you have to pay attention that gets repeated is this cout statement or the inside of the for loop, which is the thing that gets repeated. Yeah. Okay, what about this one? What's the order of this algorithm? Stuff. So again, let's try answering this question here on the right-hand side. What is the line in this thing that gets repeated over and over and over?
Cout, REI, REG.
Well, that one does not happen every single time this thing runs.
Oh, well, then
Because because of if that cout only runs when array at I is greater than array at G. So the line that actually repeated is the Boolean statement. Because every single time these for loop run, the Boolean statement will get considered, whether or not it's yours. But every single time the Boolean statement will run, regardless. And therefore that Boolean statement, the if condition, that will run n squared times. Make sense?
Yeah.
Right. But how many times the cout statement runs?
It would only run if I greater than j.
Well, the thing application I have written thing application J, yes. But even though that doesn't run n squared times, it will still be on average, if we assume a random distribution, on average it will run n over 2 times on the inner loop. So half the time in the inner loop, it will be executed. And then the outer loop tells that will rerun n times. So then you still end up with a function of n squared. Was that confusing to anybody or?
To like with the if statement and see that n have a possibility happening half the time.
Yeah. Well, the
That's like
cout statement
that.
has it half the time. The Boolean statement will happen every single time, regardless. So it doesn't matter. The cout statement actually doesn't matter in this particular case. The one you want to keep track of is actually the if statement. So when you see a setup like this, you just calculate for the if statement alone. You're saying that that Boolean will happen all the time for the for loop, regardless. Right? So you automatically dealing with n squared the same as last time. Okay. Regardless, the cout statement technically won't run that many times. It will run n squared on 2 times, assuming a random distribution. All right, let's try this one then. No if statement this time, but where J started from is a little different.
I still think is n squared.
Still think is n squared.
I'm trying to understand why.
So again, okay, I think I'll work this out, right? Because sometimes it's a little hard to see. So I'll tap out of it. And let's use mathematics.
N multiplied by n plus 1. So count to like n squared plus 1. And then you just ignore the 1. So it's bn squared.
It's a little too, no, not quite. So what you want to do is you want to start with the inner loop, right? So to start with the inner loop, let's say I is 0. So when I is 0, how many times what values of J does the inner loop run for? When I is 0, what are the values of J? Zero. J is, what are the values of J?
Will be 1.
Yeah, well, J will start from 1, but what are the values it will take?
Only
Loop.
integers.
That'll be 2, 3, 4, all the way up to size 1. Yeah, all right. When I is 1, what are the values of J? Okay, suck at this.
Start from 2 and continue on as
2,
in
3, 4, all the way to size -1 again. All right, nice. So I equal 2 now.
Yeah, 3 and the rest are integers.
Cool, so far so good. 3, 4, 5, all the way to size -1. Okay, cool. So let's skip ahead. Let's say I is equal to size minus 3. What's the value of G?
Size minus 2.
Size minus 2 and size minus 1. All right, so last one then. When I is equal to size minus 2 then, what values of J are there?
Size minus 1.
J is equal to size 1, just one item. Yeah. Okay, so how many times did the cout run for this iteration of I? Just once, right? When I was size minus 2, it will run once. Yeah.
Yeah.
Okay. What about for size minus 3? How many times will that run?
Run twice.
Twice. And then size minus 4. 3
3 times.
plus 4 plus 5 plus all the way plus. Okay, how many times did it run here? The first time, fine. Size minus
Size
1
minus
times.
1 time. Yeah.
Size minus 1, right? So therefore, the number of times cout runs, or the number of times cout executed, is the sum of this expression, right? 1 time and 2 times and 3 times and 4 times, blah, blah, blah. So how much is that in total? Okay, so using recursive whose rules will format to one of them. If you add this to size minus 1 plus size minus 1, and then they keep here now. You add this 2 to the size minus 2. 2 plus size minus 2 plus 3 plus, okay, I'll move this across, so I have more space to put size minus 3 plus onward. How many of these sums are there if I pair up each one of these? 1 went with size minus 1, 2 went with size minus 2. These are pairs, right? How many in total were there? How many numbers were there in that summation? Size minus 1 numbers. Lost you or no?
Okay, so the curse size minus 1 2 times. Those
Yes.
pairs.
So this is the pairs happen size minus 1 on 2 times. And then if that occurs that many times, what is this equal to, the summation? 1 plus size minus 1 is size. 2 plus size minus 2 is size. 3 plus size minus 3 is size. So that means size occurs that many times. Okay. So this is actually size squared minus size on 2. Following logic there. So this is order what? And now we have this expression, right?
Right. N squared minus n.
But n squared minus n is
I think
just n squared.
that's n squared.
Yeah, because the dominant between those two is the n squared. So it will perform a little bit better than n squared than a straight up n squared, but it'll have the same order. Okay? Because of the constants as well. So this one is actually, yes, just order n squared. That's how you arrive at the order n squared here. Again, you just have to kind of sit down and write out the values. This is why I'm trying to get you at trying to write out the values themselves for the loops. So when you see people do this kind of funny business, you just kind of figure out, well, your whole one constant that's so I at 0, what are the values of j? When I is 1, what are the values of j? Yada yada yada. And you will come up with something like that, right? Here. Right, only 2 more I had prepped for this thing. Oh, this one.
I think it's like 1,000 n squared, and it's come back to n squared.
Pretty much, that's it. So you see this inner loop only depends on a constant, right? So therefore this also happens at constant times in this inner loop, but that wouldn't matter because when you do the constant times the n squared, you'll still just get the n squared, right? Obviously this would be worse than the n squared minus n on 2, right, from before, but again, same order, same group order in a nutshell. Right? All right. Last but not least, recursion. Any ideas how we're going to tackle this? Kill this in a moment. So I'm making the assumption at the moment that you all can do all this thing. Recurrent relations from maths. I think that's a year 2 thing at the moment. You all remember recurrent relations from math? But I assume you remember this token swivels. So what I'd say is let's try to write a recurrent relation for this. So let's start with t of naught, right? How much time when n is 0 will this function take? In terms of
It only take one time because the statement, if statement, they would basically declare 1.
Well,
If
I'm
it
doing
is
it in
checked for
terms of
0.
this thing on the
Oh.
right hand side here. So what would it be? First you have a boolean, plus a b, and then you have return, right? That's b plus
Mhm.
r. Cool. What a time for 1? How much time will it take then?
I think the same time b plus r.
Really? Yeah, it wouldn't start from here. So you'll check this
Oh, wow.
boolean, it wouldn't be that, and then I'll check this boolean. So that's 2 booleans and then r. That's
Okay.
2b plus r. All right. So what about t of n? Where n is greater than 1, obviously. Okay, let's do 2. Make life easy. When n is 2, we will do what? 2b, check, 2b plus this times that, so that's not multiply, m, right? Plus, you'd have this subtraction here, the n minus 1, m plus s, plus the call to the thing and return, right? I'll just summarize that as a single R. No, it wouldn't be exactly that, but whatever. We'll do m plus s plus r just for simplicity's sake. That makes sense? And then the m plus s, remember this has a call to the factorial of 1 at that point, right? So that's actually plus t of 1. Make sense? So t of 2 is actually that thing. What is it?
For tier 3b, it'll be like 2b plus m plus s plus r plus
T of 2.
or t2.
T of 3 would be 2b plus m plus s plus r plus t of 2. Because then you'll be calling the factorial of 2, more or less. That most of the time that takes. Yeah. So I could generalize this at this point, right? So I could say t of n is 2b plus m plus s plus r plus t of n minus 1. So far so good?
Yeah.
All right, cool. So I'm going to just put my recursive solutions like here. And what I'm going to do is I'm going to transpose this thing to the other side, right? So I'm going to cut you from here, put you on the other side. So the plus sign becomes a minus. Yeah. See what I'm doing here, right? Let's put you over on the other side. Just minus. Cut you from here. Put you on the other side. Plus sign becomes minus. Right. I'll just write in at least one extra one, just sort of. I'll look a little bit more about it, right? 1 minus 2. Yeah. Okay. Nothing magical so far. Notice these things going on the road here. What would happen if I added up all of these here? What would happen? You have a minus tn minus 1 and then a plus tn minus 1. I have a minus tn minus 2, and the line before that would have a plus tn minus 2. Right? So then this one will cancel with this one. This 3 will cancel with the 3 that would be my line below that, right? I could write an extra line just so you could see something better. 3, yeah, I just write it in so you can actually see it, right? 4, 3, 4, 5, 6, 5. So you see how it's recurrent? This 2 will cancel with this 2. This 3 will cancel with this 3. This 4 will cancel with this 4. 5 will cancel with this 5. Yada, 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 yada. Until the n minus 2 from this line will cancel with n minus 2 from this line. And the n minus 1 from this line will cancel with the n minus 1 on this side. So if I add up only the left-hand side, what expression do you expect to get? Or when you're adding up these, right? So if I add up on the left-hand side only, what is the final expression I'll get if I add up all of those? Because I'll be canceling this. Again, 2 will cancel with 2, 3 will cancel with 3.
So you would
You would end up with what?
get t to the n minus t minus T1.
minus T1. Cool. So that's the left-hand side. Over the right-hand side of the equal sign. It's just this thing over and over and over, right?
So
Okay. How many times
and
does it
by
occur?
I think n times.
Well, this is n and it goes down to 2. So it's actually n minus 1 because it all T1, right?
Oh.
Yeah. So I'll just write that in as n minus 1. And then I'm multiplying that by the expression, which is 2b plus m plus f plus r. Right? So the math there. Cool. But we know what T1 is. T1 is actually 2b plus r. Yeah. So I can say T of n is equal to n minus 1 by this thing, 2b plus m plus s plus r plus T over 1, which is 2b plus r. Yeah. So after all that pain in the buttocks there, we have this expression for T of n. So what is the order? I mean, I can simplify this down a little bit, but T of n is what scales with respect to n? This thing scales with respect to n, and it happens n minus 1 times. So the order is
It's just n.
order of n, pretty much. Yeah. So when you write a recurrence relation, when you write a recursive function, it will always have this kind of thing, right? Where you could write it as some constant or some function plus the time of the previous run, right? You could always end up with that. If you use the same kind of method where you just take the time of the previous run, put it on this side, and just add them all up, you'll always get something that looks like that, right? Well, that's most simplistic ones, right? There are other ones, but you'll have to use other kinds of recurrence analysis. I won't probably give you more than a tail type recursion, which will boil you down to something like this, really, truly. If I was asking it up in an exam, because I think that's just all we get. If I were to give you a more complex recurrence relation, right? But yeah, this is just an idea of how you would analyze the complexity of a recursive type function, right? So everybody good? That's the
Yeah.
end of a basic intro to algorithmic analysis. So if I gave you a piece of code, in theory, you probably could analyze it, right? And there's actually a couple of these in your lab too to analyze. I think I'll give you like 5 or 6 to analyze. They'll all be roughly around the same level of difficulty. Well, you could do a microanalysis or you could do a macroanalysis. But sometimes when people do the macroanalysis, they might make a mistake. So sometimes it's a good idea to default to the micro until they get a little bit more accustomed to doing this kind of analysis. Right? So that being said, let me ask you one hard one. So if I had to order, just to test and see if you get the idea of 2 to the n plus n to the 1000, what's the order of that? As of just a random question.
It will be an order of 2 to the n.
Yeah, because it dominates the polynomial time one. Right, cool. I'll make sure you got the idea. Once you can see that easily, then you basically have the rough idea on how to do something like this. It doesn't get more complicated than that. It's not very sick of this course, at least. Good. So stop the share at this point. Stop.